Hello, guten Tag. My name is Bram. Although I am now an IT engineer, I went to school to university to become a molecular biologist. Back in the days when big data was still something that wouldn't fit in even an Excel sheet. So I created 200, 300,000 data points a week, which turned me into a statistician or a bioinformatician. If you're in an academic world, you're also the server guy. So I learned Puppet along the lines. And in the end now I'm a DevOps cloud consultant or buzzword bingo engineer at the factory, which is a consultancy company in The Hague, in the Netherlands. And to start off my presentation, I would like you to think about the following number: 29.74 seconds. Is it a very weird SLO and service level objective? No, it's actually the amount of time this guy spent in the 2012 Olympics to become Olympic champion. There's 3 runs, 30 seconds, the guy had a gold medal. Of course, that's when we think about athletes. What we see is the matches or the tournaments, but then that's not what an athlete is. This is an athlete. He's retired right now, but he's spent an incredible amount of time training, getting his body ready, getting his mental state ready. So when we think about athletes, when we think about musicians, this is actually what they do most of the time. They are somewhere in a back room, they're training very hard. Just to produce 30 seconds of work in a 4-year span. So for them, it's high pressure, right? We practice 4 years for 30 seconds worth of gain, and that's something that was described before by a guy called Malcolm Gladwell. He said it takes about 10,000 hours of practice to become an expert. That's not actually what he said. It says experts have on average spent 10,000 hours to gain their expertise. So when we continue looking at athletes, especially athletes, teams, they also review their training or their matches. They spend nowadays, this is a picture from a movie called Moneyball, and this is where first statistics became a big thing in baseball in America. This was a team of 2, a trainer and a statistician, that basically worked out whose people weren't performing best at the moment, who had the most potential to perform well. So they could buy them cheap and then get them to the point where they needed to be. And if you start translating this to engineering, to IT engineering, then when I started, it was basically someone tells you, build me a web server or build you a statistics platform, what we now would call a data lake. That's what I was asked to do. But they don't actually ask you the follow-up question. When I went back to my boss, he never asked me, do you know when it's broken? No, of course I didn't know when it was broken. I knew it was broken when my colleagues were saying, I can't get to my data. And when in IT, it's quite common to start learning. They basically sit you next to the grumpy guy in the basement who's been there for 20 years, and he's teaching you whenever something goes wrong, he'll teach you how to fix it. But actually, that's a very bad model of learning, because either he's been there for 20 years and he fixed most of the problems. So as a newbie, you won't be exposed to all the problems you need to learn about. So you'll only learn about things the grumpy guy in the basement basically didn't know enough about to fix. Because it's reoccurring. So it's actually, for IT, that's the worst teaching model I could find, basically. So not only do we need to have a somewhat broken teaching model, we apply the same principles to building our monitoring stack, or what we, in the buzzword bingo world now, call the observability stack. So we'll collect our logs, there's a big data lake, we'll collect our metrics sometimes. if we're really cool, we'll also turn on Jaeger or Zipkin, and then we'll do traces on whatever we manage to implement tracing on. If you're PHP, you are, pardon my language, shit out of luck. If you're on Java or Golang, you're good. Better, not good, better. So that's what we built in. But actually, if we go back to firemen, go back to pilots, they don't throw you in the deep. Pilots most of the time spend their time in an simulator. That's why they learn. That's why they learn to fly. If they trust you to fly the simulator properly, that's when they expose you to a plane. Whereas when you're an intern, you're basically, you're there for 3 weeks, and congratulations, on call. Your first on call is next weekend. But people react very badly to stress. And that's why especially firemen don't get exposed to real fires immediately. They train, as a nice example, they train at a simulated fire. Because if firemen make a mistake, people die. Most likely themselves. So they want to train these people to have a proper response to adversity. So they need to have their breathing under control. They need to have their brain in control. So that most people, a very significant section of people will freeze up when they see problems. Especially when I mentioned on call, that's the worst time to actually be engaged with a problem. Right? You're in deep REM sleep. That's when you get woken up, and that's when you get asked to look at all the blinking lights to work out what the solution to a problem is. Right? You get pulled out of caveman mode right into, brain needs to be activated mode, which is, again, silly. Right? We need to train this. So we need to be able to train ourselves. We need to be able to train to actually read the metrics for what they are. Right? We need to be able to see patterns, preferably have our tooling, come up with this is probably a pattern that I've seen before and that was related to a problem. Right? So then you can automatically go further. So to do this, pilots also spend a significant amount of time on checking lists. Right? There's a lot of buttons they need to turn on. There's a lot of components that need to work. So what they've done is, it's a repetitive thing, right? You go into a plane or sometimes a bus. Well, not for pilots in a bus, but bus drivers have the same problem, but it's more contained. Like, it's very complicated to turn on a plane properly. And if you do it every day, then you're probably going to skip steps. So what pilots are forced to do and force themselves to do is basically have a checklist, right? So and we should be doing similar, what we call run books, right? Have stuff ready, even though you probably know the solution to the problem, how to do it. Write it down. It helps you to get your ISO certification, but it also helps 3 a.m. you that just woken up. And then the next continuation is game day exercise. So we have exercises, but they're mostly synthetic. Right? It's a problem we've had before. It's a problem we imagined that we would have. And this is a picture, and there's a link to a video of a bridge, the Tacoma Bridge in Seattle, and it was beautifully designed until they exposed it to wind. And then it turned out that the oscillation of the wind was the same as the oscillation of the bridge, and it started wobbling and it broke down. Nowadays, architects know this stuff, and they basically, when you build a bridge, this is something gets tested, right? What would be the oscillation and what would be the wind force that would match and would break the bridge? If we start translating this behavior to engineering again, let's start doing chaos engineering. Chaos engineering is also a new buzzword name, and I found the definition and I highlighted the 3 words that I think are really important. when we test ourselves, when we train ourselves, the end goal should always be to have confidence in production. That it either stays up, or that it does exactly what we need it to do, or that what we expect it to do. Because at the moment, when I started IT, like web servers were fairly simple, it all ran on the same node. But now when we start doing containers, when we start doing microservices, there's so much stuff running that we should assume that probably something is broken at any given time. That also maps nicely to promise theory, where I promise to clean my room, but it probably isn't. So all the other components should have a built-in fail-safe mechanism to be able to cope with this degraded state. And not only degraded state is fine as long as we can work around it. So our monitoring should also be able to pick up subtle things. Right? CPU at 100, that's very simple to work out. Probably CPU at 100% might not have business impact. The fact that I see the ratio between HTTP 200 and HTTP 500, if I see that ratio change, that probably is a problem. But that's a derived number from a derived number. So we need to be more subtle in whatever we do. And that's something we need to train ourselves in. Right? Because whenever we go on the internet and go, I want example monitoring stack, that's basically what they stop. Like CPU, RAM, it's important information, but it's not necessarily business information that they're using. And as I said, firemen, pilots get trained for failure. Not only do in these simulators, they teach them how to fly, but they also inject weird behavior. Like they inject failure to see how people respond. That, as I said, that's something we need to learn to react to, but it's also something we need to learn to cognitively deal with. Right? Can we see a problem? Can we break it down into little problems that we know the solution to? It's basically math. Right? Math is the same way. You break it down into a formula you know, and then you combine the formulas, and then in the end you have the answer. So we need to teach people to be comfortable with facing failure, so that we. And yes, it deliberately runs off the edge of the slide. So that we teach them that there is a problem, that the problem is going to be fine, but that you're in charge, and that not only you are in charge, your team of colleagues is in charge of working out what the problem is. And depending on influences, that it's allowed to run for a certain amount of time. So if we're looking at more chaos engineering, turn that into something, DevOps is not about tools, but it's always nice to mention one. The granddaddy of chaos engineering is a tool called Chaos Monkey, came out of Netflix. Unfortunately, they don't seem to develop it anymore, but that's basically where a whole ecosystem built out of. And what it does, it runs in your production environment and injects failure to not only, so that we not only be able to respond to it, but it's basically, we expect something to be in a degraded state, but because of Chaos Monkey is running, we know something is in a degraded state, so we should see something in our monitoring. Like, you don't have to inject it immediately into your production setup, but you can start with the simple test setups. As I said, it's so complex that even the complex CNCF landscape now has its own ecosystem of chaos engineering. So if you're interested, this is the little area at the bottom. That's where you need to be if you want to investigate this further. Going back to a little bit of my own science, it's always good now in the age of Corona. This is a electrophoresis gel with proteins, and the proteins are separated by size. This is one of my published results. It looks nice, but if you look at the first one, this is what it basically looks like. This is when you go to university and they tell you to do this stuff. This is what it looks like. And this is also built-in failure. If you go to university, you become a biologist, your first reports, they don't expect you to be published grade stuff. You know, even though it looks simple, it's not. There's a lot of intricate parts that need to come together. And why am I showing you these gels? It looks simple. It's 8 lanes, has some proteins on the left, some in the middle, but when you build an experiment like this, it's actually very important to think about what the data is that you want to come out at the end. My first academic supervisor told me it's 1% inspiration and 99% perspiration. So if the inspiration isn't right, then your experiment the result of your experiment is basically worthless, right? Because if we look at this further, is if I have a sample of 1, the result is invalid. Okay. Yeah, IT support, you know. In a room like this, we should be able to work to and in a talk like this, we should be able to get to the result we want. So if you look at our results and we look at the experiments we want to do, is you know, how many times do we need to do the experiment to get the result, a result that we trust? You know, when you ask a first-year student, you know, if we do it once, or if any Mythbuster fans here in the audience, you know, they do an experiment once and then they call it significant proof. Do we need to have experiments that do we need to have samples of part of experiment that we know is going to fail, right? So that we prove that the experiment we did and the result that's come out, is it actually the result that we're looking for? Is it the result of something else that just happened to happen at the same time? If I do this experiment twice, can I actually compare the results between the experiments? Because are the ingredients in gel 1 the same as gel 2? Probably you don't know. That's why you do experiments to prove that the experiments you're actually going to do are actually valid. And let's skip ahead a bit. Turns out, was this actually the experiment we should have been doing in the first place? Are we actually interested in the size of the protein? So if you start comparing this to experiments, we do this in engineering, when we start doing chaos engineering, we need to make sure that that's the things it starts to pull over or destroy are those actually the important bits that we should be testing. I've been at a customer that proudly presented to the public that they were doing chaos engineering, but internally I knew, oh yes, we do it, but we don't do it on the databases, we don't do it on the payment system, we don't do it on basically anything that was important. So yes, they did experiments, but the results were utterly useless. We can destroy, you know, one part of our Java system. It's like, okay, that has no zero business impact. So yes, we spend a lot of time on doing experiments. So we should be able to come up with an experiment on ourselves that we should be able to build infrastructure that we can destroy easily, or in the Kubernetes way, get a sidecar that injects some kind of weird behavior. If we start summarizing, what have we learned so far? When we look at athletes, practice makes perfect. And musicians, when we look further at athletes, game analytics, so reviewing incidents. For us, translating it to us, incidents, reviewing incidences, and learning from incidents really helps. If we look at pilots, doctors, firemen, we need to make sure that when we're in an incident, we need to be the relaxed version of ourselves, and we need to really test in life-like situations. And if I want to focus on the scientists, lies, damn lies, and statistics is basically the one to look for. Is our experiments, the experiments we're running, the training modules we're running are they good enough for what we actually want to learn about ourselves, or the business finds important about our platforms we're running. To quote myself, checklists are incredibly boring. So we've made a list, we've looked at other people, but checklists are incredibly boring. So let's, again, look at how it could work for ourselves. Get game day exercises going. It's a great teaching moment, and if you who don't know what game day exercises are, it's basically we're gonna destroy our platform on purpose. Preferably not prod, but you can start on either your test or if you have configuration management in place, because some of these experiments are definitely destructive. So I need to build them quickly, I need to load data in them, representative data into them very quickly, and I need to be able to recover. So that's one arm, quick, up and down, and also the observability that we discussed before. So I need to have metrics coming out of it, I need to have logs out of it, I need to have traces out of it. And it needs to happen automatically. Because if I build this up and I send a ticket to whoever is running my metric system, and it takes 4 weeks for them to add the node is already long gone. So it needs to announce themselves into monitoring systems immediately. And of course, if you really live in the year 3000, you start introducing it in prod, and you basically make sure that your system is in a known degraded state, or not even a known degraded state, but you are aware it's in a degraded state. And we can actually convince management that failure is normal and expected behavior. We cannot assume 100% uptime. Of course, every boss is going to yell at, I want 100%, but 100% is not possible. It absolutely is not possible. Again, going back to the promise theory. We promise something to be up 100%, but it's never going to be up 100%. You know, hard disks die, entire data centers catch fire. It's normal and expected. So we also need to have engineers be scientists. So we need to train them, we need to test them, and if you do it the right way, it automatically turns into monitoring. So that's something you can use later on in production, or the other route. So I have a working production monitoring system, and I onboard new people. I'll have a game day exercise with an exercise that I know the results will be coming out of my monitoring system, because we added them the last incident that we're now replaying for these new recruits. And if we put $new thing into service, are not satisfied, and push your bosses not to be satisfied until you have real definition of done. And the definition of done basically means I have reasonable metrics, I have reasonable logging. I also have a service level objective and indicators to work out if it actually is running. And I need to have run books, or whatever you call them. So when something goes wrong, I can fall back. 3 a.m. me can fall back to something I've written before, and there's a 10-step process to recover my SQL data master replication. And not kill both arms of the replication like I did. Right. And of course, dog food your own stuff. So make sure that your monitoring system also can survive failure. So most of the time we'll think about our application being in 2 data centers, and we can lose an entire data center, but turns out your Prometheus or your Loki or whatever you have running is single instance. So make sure that you build those out as well, that you can lose an entire data center there as well. And that's how you can train your new recruits without actually affecting business. But you know that the tools that are going to save you at 3 a.m. in the morning will also be in a usable HA state. And that's the end of my presentation. Thank you.